Now recording. Okay, so this is the last lesson that is relevant to test 2. So we're still dealing with first order equations, like the ones shown last time, for which a method of characteristics was used to obtain a solution. So we're still going to be working with that. The difference is now we have nonlinear first order PDEs instead of linear. And they're going to be based on conservation laws. And there's going to be an interesting real-life application to this, one that I've actually personally witnessed in action out in the real world. So I'll be able to tell you about that after I cover these things. And that application is traffic flow. So the meaning of a solution in this case, U of xt, is representing the density of cars at any point along the highway, which is referred to by x. So since it's a road, and we travel in one direction, so that makes it a nice one-dimensional problem. It's convenient at a given time t. So we're just like assuming it's a straight road. So if we look at some segment on the highway, so from literally point A to point B, and we integrate the density of cars over that interval, then you can think of it as sort of like a mass equals density times volume, where volume in this case is a one-dimensional entity, it's just the length of the segment. So if we take that integral, so you think of it as the total number of cars within a segment, but then take the derivative of this entire integral with respect to time, then that has to equal the difference in flux. So flux is cars per minute passing the point x. So we have cars that are entering the segment. So what we have here is cars that are adding to what's in this segment. And then we're deducting this term corresponding to cars leaving the segment, so we're passing point B. Okay. So this conservation equation is what we're going to use to define a PDE that models traffic flow. All right. So the idea is on both sides we have total number of cars within the segment, rate of change of that with respect to time. That's what both sides of the equation represent. The conservation law says these things are equal. Okay, so now to obtain a PDE from this, what we'll do is, and the same kind of thing was used to derive a heat equation way back early in the semester. When you have a difference of function values, same function evaluated at two different points and subtracted, you can always write it as an integral of the derivative. So that's what we're doing here. So f of a minus f of b, you can think of it as the integral from b to a of a derivative, df dx. But the integral from b to a can be written as the integral from a to b. In other words, you're swapping the limits as long as you introduce a minus sign. So swapping the limits, as you know, in Cal 2 changes the sign of the integral. And this is helpful because now both sides of the equation are expressed as an integral from a to b. On the left side, the differentiation with respect to time can be moved inside the integral. We're allowed to do that because the limits of the integral do not depend on t. in both cases, we've rewritten both sides to get something in this form. So now we have an integral from a to b on both sides, so we can rearrange that. Let's put this part on the left side. So now we have this. So the integral from a to b of ut plus fx equals 0. But the segment AB is any segment along the road. So anytime we have a situation where the integral of some function over an arbitrary segment, or an arbitrary domain, is equal to 0, the only way that can happen when the segment is arbitrary is for the integrand itself to be 0. And this is a standard technique in deriving PDEs from conservation laws. Conservation laws are often either described or can be described as integrals. You have an integral being 0 over an arbitrary subdomain, therefore the integrand is 0. So then you take the integrand and set that equal to 0, and that's the PDE that pops out. These same ideas were used in the derivation of the heat equation. You can compare to that. So a lot of PDEs are derived this way. So now we have, so this is a typical form of a conservation law. That, so what we have here is that the time derivative of whatever quantity you're tracking plus the flux associated with that quantity, its derivative with respect to x, is equal to 0. So there are a number of PDEs that fit this form for different flux functions f. So now we're going to try to solve this somehow. So we'll make an initial value problem out of this. So the PDE is defined on the entire real line. Oh, something weird is happening here. The room from the coast is back. So, not sure what's going on there. Oh, there's nobody in that room. Okay. I mean, well, I keep going without disruption. I'll just go ahead and do that. So. All right. Okay. And then we assign initial condition. U of x0 is some given function phi of x. Okay. So what can we do to solve this? So first we have df dx. So we can rewrite that as df du du dx by chain rule. So in other words, f is a function of u. And that derivative, df du, I'm going to call that g of u for convenience. And they're going to give an example. If f of u is equal to 1/2 u squared, and g of u will be the derivative, which will just be u. And that's from a specific PDE. This is known as Berger's equation. and this is something that I often get embarrassed about. I can never keep straight if it's like if the person that it's named after is, oh, I got it right, yeah. If it should be Burger apostrophe S, as in other words, the person's name was Burger, but no, it's Burgers. So I had a reviewer pop me on that once, and they had it wrong. Like, all right. Okay, so this is a particularly well-known conservation law, very closely studied equation. Who is? Don't call me. Why are people calling me? Okay. That was really weird. Okay. We have no more weird things happening today, or during this class period. Okay. So now that the PDE is in this form, the reason why that was done is to make it fairly similar to the kind of PDEs that we saw last time, where we had some coefficient times du dt plus some coefficient times du dx plus some additional terms, and that set up for use of the method of characteristics. So here we have, again, a term involving ut, a term involving ux. The only differences between this time and last time is that the coefficient of du dx now depends on u, thus making the PDE nonlinear, whereas in Monday's material, those coefficients of ut and ux were only allowed to be functions of x. So that's a situation of that's a case of a linear PDE. Okay. So now, here are the equations that the method of characteristics, same as last time, would give us. That dx ds is a coefficient of ux, which is g. Now g is a function of u, but u itself is a function of our characteristic equation, our method of characteristics variables, tau and s. Same meaning to those variables as last time. And because the initial condition, as usual, defined on the x-axis, our initial condition is x of 0 is equal to tau. So tau indicates a place along the x-axis for each characteristic curve to begin. And then the coefficient of du dt is just 1, so dt ds is 1. Because the initial condition is on the x-axis, t equals 0, the initial time. T of 0 is 0. So now, we go back to our PDE, so we have ut plus gpu ux. Well, that's the same as du dt dt ds plus du dx dx ds. Because of what we have here, these derivatives built in here. But this, by the multivariable chain rule, is du ds. And from a PDE, all of this was set equal to 0. So this, right here, du ds equals 0 is what the PDE reduces to in our characteristic variables. Can't get much easier than that. And then the initial condition comes from the initial condition from the PDE. U of tau 0 is 5 tau. So recall that the original initial condition is right here. U of x 0 is 5x, so that gives us u of tau 0 equals 5 tau. So basically just replacing x with tau in the initial condition. So we have right here. So now things proceed, at this point, things have to proceed a little differently than what I showed you on Monday. Because on Monday, with the linear problem, you could solve the ODEs for x and t first. Why? Because they had no dependence on the ODE for u. So you go ahead and solve those, and that helps you write the solution u as a function of x and t. Not so anymore, because look, the ODE for x depends on u, so we can't solve that until we know what u is. This is an artifact of the PDE being nonlinear. It creates this complication. But it's not much of a complication in this case, because at least the ODE for u is as simple as it gets. All this is saying is u does not depend on s at all. So as far as s is concerned, u is basically a constant. So, really, okay. I need to make this explicit here. The solution of the IVP that we just obtained, UDS equals 0, U of tau 0 is equal to 5 tau. Is U of tau S is equal to just the initial data, 5 tau. So if your ODE says that the derivative of your solution with respect to your variable is 0, that's just saying that the solution is equal to the initial data. So now wherever we see u of tau s, we can replace it with 5 tau. And I'll just make note here that this happens to be equal to u tau 0. That's why it's the solution. And that's what we use down here. Because dx/ds is supposed to be g of u of tau s. But u of tau s is equal to u of tau 0, so I filled that in here. And from its initial condition, for u, we fill that in, it's g of 5 tau. So this simplifies things greatly as far as the ODE for x is concerned. And the reason why is because this right-hand side of the ODE does not depend on s at all. Remember, this is an ODE in s. So we had this ODE, the right-hand side depends on s and who knows what possibly complicated way. In general, this ODE could be extremely difficult to solve. It just depends on the functions g and u. But because the right-hand side, which at first appears to depend on s, actually turns out not to, now it becomes almost the simplest ODE we can get. I say almost because this is the simplest ODE we can get. This is only slightly more complicated. Because what we're saying is dx/ds is equal to a constant. So now, what that means is we can just integrate both sides. If I take the integral of both sides to get x on the left side, what do I get on the right side?
You get 0?
What?
You get 0?
No, that's differentiated. We integrate, but keep in mind, this is an ODE in s, therefore you must integrate with respect to s. If this is a constant, in other words, it has no s dependence, what happens when you integrate that with respect to s?
You just get
Almost.
or like a constant.
Yeah, constant times s.
Yeah.
This constant. So that's what you have. This whole constant times s. And then a constant of integration. So we do have an additional term that you can think of that as the plus c when you integrate. And to figure out what the plus c is, you go back to your initial condition. So now, if I said s equals 0, I need to get tau, so that's why I have tau here. So now we've solved the ODE for x. And then the ODE for t that was right here, that's also easily solved, and we have that. Just like in the examples from last time. So one nonlinear PDE was broken into 3 not so threatening ODEs. Are there any questions about these 3 ODEs? I know one of the common and also justified non-sequence mathematicians is they tend to say, oh, this is simple, this is simple, this is simple. And which might be unsettling if what we're looking at doesn't appear to be simple. But I guess the way I look at it is to prevent something that students do all the time, and that is overthinking things. So whenever I say something is easy, I mean, there's not supposed to be a whole lot of steps to it. That doesn't mean I expect it to be easy for you to grasp right away. That can still take time. But math is a mix. There are some problems that really do take a long time to slog through. And then there are some that don't. So these 3 individual ODEs fall in the latter category. Something to think about with regard to this ODE right here, right? It's weird to think of this as like treating it like a constant because it's obviously not really a constant, it's just something that doesn't depend on S. And this is an ODE in S. So you see something like dx ds is equal to 3. It's easier to make that leap, say, okay, then the solution is 3s. Because it's something that is glaringly, obviously a constant. It's difficult to think of this in the same vein, but it really does work that way. And so the thing to keep in mind is that what helps you make the leap from simpler problems to more complicated ones is that you really are applying the same rules. That's one of the nice things about math, one of the few nice things about math, is that rules are absolute. And it might seem like you're now in suddenly a very different situation from what you were before, but once you realize that you're really not, it just appears to be different. But in terms of the rules that you follow, it's the same. And that's what helps you make that leap. Okay. So now, okay, U has already been worked out earlier. That's what we have here. U of tau S is 5 tau. But like last time, we need to write this in the as a function of x and t. Unfortunately, that's going to be more difficult than before. If we go back to this equation, okay, x is equal to tau plus g of u times s, then I can rearrange this and solve for tau. So from this equation, I have tau is equal to x minus g of 5 tau times s, but phi of tau is u, so I can fill that in there. And s is t. So expressing this in terms of the original variables x and t gives me this. And now I can take this and substitute it for tau in here, and this is my solution. So u of xt is the initial data phi, but evaluated at x minus g of u times t. And sure enough, if you set t equals 0, you just have 5x, which is what you expect, because that's the initial condition. But the unfortunate thing about this is what is known as an implicitly defined solution, because u appears on both sides of the equation. So in other words, you can't just plug and chug to get u of xt is equal to something in a particular x and t. If you plug in a specific x and t, you now have an equation that you need to solve to get the value of u. And that equation might be algebraically intractable. You may have, like, it may well be that the only thing you could do is solve it, like, numerically. Like using some sort of iteration, like the ones I teach about in numerical analysis classes. So we have that letdown. And we're on our way to a solution formula, much like the examples from Monday. And we get to the end, and yes, we do have a solution formula. It's just one that's not so practically used. Depending upon a particular function phi and g, it may be possible. It's just problem dependent. Now, as far as working out problems of this type, fortunately, at least to get an implicit solution, that can be done quickly, because if you are given a conservation law, in other words, if you're given this problem, and you define g of u to be df du, because you're given the PDE, therefore a function f would be given, then you can get g. And then what you can do is skip over everything I've just shown you, because I'm showing you how a solution is obtained, and jump directly to this. So the solution is always, for a conservation law, it's always your initial function evaluated at x minus g of u times t, where g of u is the derivative of your flux function with respect to u. Any questions about solving this kind of problem? In other words, you don't have to go through all the method of characteristics rigmarole. Now, for those kind of linear problems from last time that are not of this form, yes, you do have to do that. But if you're given a PDE that can be described as a conservation law, ut plus fx equals 0, where f is some function of u, then you know that this is your solution. Each time on a test. Now, even when you don't have a solution formula, you can still figure something out about how the solution behaves. So at any point along a real line, on the x-axis, that marks the beginning of a characteristic curve. And the idea is the initial data propagates along the characteristic curve. And in this case, because du ds is 0, not only is it propagating along the curve, it's not changing as it moves along that curve. And we can write down the equation of that curve. So we can describe t as a function of x, and it involves this function g that comes from the PDE, at least as long as the quantity is non-zero, of course. Well, in that case, if it is 0, then we have the vertical line. So this is something you can do in general for any conservation law. That this is the equation of characteristic curves. I'm pointing out because I get a problem on a test or homework involving solving a PDE based on conservation law, that's something that can be asked. What is the equation of characteristic curves? We already have it right here. Now, if you think of this kind of like the equation of a line. All right, equation of a line, you're accustomed to y equals mx plus b. Well, here, t is playing the role of y. So you can graph your characteristic curves in the xt plane. So what that means is, if you think of it as like, instead of y equals mx plus b, it's t equals mx plus b. Well, what's the m? Well, the answer is it's what's multiplying x, which is 1 over g of 5x naught. So that gives you the slope. In other words, each characteristic curve is a line for this kind of problem. And this is a slope. Now, here's where things get dicey. Because what you have is some line starting at this point. And it's going to go up into the xt plane. And it has this slope, 1 over g. Along that line, the solution is equal to the value of phi at that point, 5x naught. So it's like a value, 5x naught, is being carried along the line starting from this point. But we could have a situation, because each line has a different slope. What if, for example, it's supposed to consider 2 points. So what could happen is, suppose the slopes in both cases are positive. What can happen is, if the point to the right has a much steeper slope than the characteristic curve from a point to the left, lines will eventually cross. Now, along those lines, the solution is equal to whatever value the initial data had. So if you have 2 points, like x0 and x1, along one line, the solution is equal to 5x naught. Along the other line, the solution is equal to 5x1, and these values can be different. For a linear PDE, those lines are guaranteed never to cross. But for a nonlinear PDE like this one, they can. So what happens? These points intersect, and the solution is now expected to be equal to 2 different values. In other words, the solution becomes multi-valued. That's bad. And that is what is known as a shock. So this is a well-known, well-studied phenomenon associated with nonlinear PDEs, where a solution develops a discontinuity at a point because of these characteristic curves crossing each other. Actually, I want to check. I'd like to give you, if possible, a visual of this. I'm going to check the textbook to see if they have. Looks like, I think we do. Let me see what's given here. Yes, I can show you that. All right. Oh, but before I do that, once a shock occurs, then this continuity is going to start traveling from that point where a shock happens with a constant speed that's given by the difference of f values between the 2 conflicting values of the solution divided by the difference in those values. In other words, it's a slope that indicates the speed of shock. And this here the speed is dx dt. So this difference quotient is describes how the solution behaves once a shock occurs. And now I will give you a plot of this taken from the textbook. So I need to unshare and reshare. Well, I need to. Okay. Okay. All right, here we go. Let's make this a little bigger. All right, so what we have here is the xt plane that I've been describing. And here, the initial data is specified here along the x-axis. So your 5x. And what we have here are the characteristic curves that emanate from the x-axis with a given slope. And actually, so the problem in this case, let's get to the PDE. Oh, okay. Here we have initial data that is piecewise defined. So it's equal to 1 up to a certain point, and 1 minus x, and then 0. So this is what the initial data looks like. So it starts out at 1, decreases linearly down to 0. Now, the consequence of that initial data is shown here, that we have these slopes. Okay, so in this case, the slopes are equal to 1/2. But then, at some point, the slopes get steeper and steeper. And that causes these characteristic curves to collide at this point right here. So that's where a shock occurs. Once that shock happens, then discontinuity appears in the solution. Like if you were plotting the solution at different times, you'd see a wave propagating, like in this case, from left to right, and it would start, you'd see a jump that would keep moving at constant speed from left to right. The 1/2 comes from the fact that this is the PDE in question. UDT is 2u ux equals 0. So that 2, coefficient of 2 shows up down here as a result. Okay, so this is the kind of behavior you can get from these solutions. And you can tell because of the equations of these characteristic curves. You can see, like, okay, for certain points, the slope of characteristic curve is steeper than points to its left. Once that happens, then a shock is going to occur. On the other hand, suppose as I move from left to right, if the slopes were getting smaller, less steep, then you never have to worry about characteristic curves crossing, and a shock would not occur. So really, it's when the function, when the function g, when it's getting smaller as you go from left to right, meaning that the slope is getting larger, that's when a shock can occur. Any questions about this behavior that we're seeing here? So I want to tell you about a time where I actually observed this behavior in real life. So this is a few years ago. Oh, I guess 4 years ago now. I was driving through Houston. So I'm on one of our interstates. It's probably I-10, and the traffic's pretty busy. It was around evening commute time, and so traffic was heavy, but still moving along pretty good clip, like around 65 or so. Now, if you've ever experienced this happening where you're on an interstate, in a larger city like New Orleans or Houston, and traffic's moving along pretty good, but all of a sudden, for no identifiable reason, slows to a crawl or even a dead stop. There's no accident, there's no construction, nothing like that. Things just slow down. And like, why? What's going on? What's wrong with people? That is a real life example of a shock. And it comes from at busy times, the more people getting on the highway and how density is evolving. There's a solution to you, the density of cars, that because it follows this kind of conservation law, that's possible for a shock to develop. And what ends up happening is traffic slows down, and then so this is what happened in this situation, that we all slowed down for a little bit, and then we started moving again. But it's different behavior than what we normally see. For example, when you are stopped at a red light, let's say you're several cars back, light turns green, not everybody starts moving, only the first car can move. It takes time for you to be able to get moving. And it's because these kind of traffic flow systems have a finite speed of propagation. That's why you have to wait. But that didn't happen in this case. We all slowed down, and then we started moving again, all in lockstep at a constant speed. Similar to what I just described. Once a shock develops, that discontinuity continues moving at a speed that depends on the difference between the bodies of solution on either side of the shock. So when I saw that happening, it's like, oh my God, this is what I teach about. That it really does obey that kind of rule. So, and the thing is, these kind of PDEs that model these situations, they're often simplifications, of course. But in this case, it describes them quite well. So, I don't know if they use these kind of traffic flow equations when planning highways and so forth. I hope so, but sometimes you have to wonder, especially in Hattiesburg, where I've driven in so many large cities, but Hattiesburg manages to have the most annoying traffic. So, yeah, so the PDs are real. Okay, so, okay. And this kind of behavior is quite difficult for solution methods, like numerical methods. Like here, the analytical method we tried, method characteristics, was helpful, but it only got us this far. It would still take some numerical work to actually be able to like visualize a solution, or even compute the solution at a given point xt. Unlike other problems we've done all semester long, where the end result is some formula, u of xt equals this, and you can just plug and chug with whatever x and t you have. But not so in this case. But the important lesson from today is that even when you don't have an explicit solution formula, you still can understand something about how the solution behaves. In this case, you start with your initial data, and that initial data is transmitted, if you will, along these lines. And you can use that information to help visualize the solution. And that would actually be more efficient than trying to solve this equation for whatever functions phi and g that you have. Because you can work out what the characteristic curves are. So here's how you can use to try to use this to figure out let's see. I'm trying to think of how this would go. It might not be as easy as I think, but suppose you have a point, u of xt, and you want to know what is the solution at this point. You'd have to know what is the characteristic curve that passes through this point. But so for this equation, if you are given x and t, then you don't necessarily know x naught. So, like where the characteristic curve starts. It's probably easier to go the other way, where if like just to visualize the solution, the easiest thing to do is choose several points along the x-axis, play your role of x naught, and then you evaluate for each such point g of 5x naught, that gives you your slope. Then you can choose several points x, and now you have the equation of this line. This is all worked out, and you get your t values that go with it, and so you can compute several points along the characteristic curve, and then you know at each one of those points the solution is equal to 5x naught. So that would be a way to like plot the solution as a surface, for instance. So even without a formula, a formula is something you can do to have insight into how a solution behaves. And that's why, and all of that comes from what we saw here, that in characteristic variables, the PDE reduces to this, duds equals 0, which says that the solution is just taking the initial data and propagating it along certain directions. Okay. So now we've covered everything that can show up on the second test. Do we have any questions about the test or related homework or anything? Okay, well, Monday is set aside for talking only about the test. Well, I mean, of course, you can ask more questions there too if you have time for any test questions. I'll be talking about the practice tests, certainly. And then a week from today, Wednesday the 13th, class will not meet. Okay, so, oh yeah.
Is the test due on the Wednesday, or do we have like a weekend for someone to do it?
Yeah, so that's something I need to check out, because normally what I do is I put out the test on Wednesday and I would do Friday.
Yeah, Friday's fine. I just took a weekend as an example. I don't need that long.
Yeah, but the thing is, it's also Good Friday.
Oh.
Now, I don't know if I like the idea of having a test due. Well, okay. I'll put out the test on Tuesday. I mean, you'll have the remainder of the week. But nobody has to work on Good Friday. Okay.